Welcome to Science Reshaped, a calm corner of the universe where curiosity drifts like starlight and the vastness of space becomes a quiet place to think. Before we begin, please subscribe to Science Reshaped and tell us where you're listening from. Knowing that these stories find you somewhere under the same sky keeps this little constellation of wonder alive. Everything we know about motion begins with a lie. We grow up believing that some things in the cosmos stand still, that the sun stays fixed while the planets dance around it, that the Milky Way has a stable heart that never moves. We picture a perfect center, an unmoving anchor holding billions of stars in its invisible grip. But when astronomers turned their most sensitive instruments toward the heart of our galaxy, toward the strange radio source known as Sagittarius A, the supermassive black hole at the Milky Way's core, they found something unsettling. Even this colossal anchor drifts. At first, this idea seemed absurd. How could something 4 million times the mass of our sun, something so powerful that it bends time itself, possibly move? Yet the evidence was undeniable. Tiny changes, barely perceptible tremors in space, betrayed the truth. Data from NASA's Chandra X-ray Observatory and the Very Large Array in New Mexico showed minute positional shifts, a gentle quivering that could only be explained by the gravitational tug of nearby stars. The heart of the galaxy, it seemed, was trembling. When the results first appeared in the early 2000s, the researchers thought they had made a mistake. Maybe their instruments were out of calibration or a distant signal was interfering. But the pattern held across continents, through years of observations and multiple observatories. Each time the measurements were compared, the same minuscule drift reappeared, only a few tens of micro-arc seconds a year, far too small for the human eye to notice, but perfectly clear to the machines. It was as if the mountain at the center of the galaxy was moving an atom at a time. Chandra confirmed it from orbit. Far above the Earth's turbulent atmosphere, its mirrors caught faint flickers of X-rays from the superheated plasma near Sagittarius A. The intensity of that light rose and fell in a steady rhythm, not random noise, but a pulse. Tiny periodic variations that lined up precisely with the orbits of three known stars, S2, S29 and S62. These giants, hurtling through space at thousands of kilometers per second, passed so close to the black hole that their gravity pulled on it ever so slightly. Each approach shifted the center of mass, and the black hole responded, drifting in slow, graceful oscillations. The Milky Way's core, it turned out, was not a static throne, but a living system. Its massive heart swaying to the gravitational music of its neighbors. At the Max Planck Institute for Extraterrestrial Physics in Germany, astronomer Reinhard Genzel and his team began 2 decades of patient watching. Using infrared interferometry, they followed those same stars around the dark center with millimeter precision. As S2 completed its 16-year orbit, the team noticed how the position of the black hole shifted slightly each time the star swung nearest. Tiny but predictable movements that repeated with each pass. Genzel would later win the Nobel Prize for proving that Sagittarius A was indeed a black hole. But he often said the most haunting discovery was seeing that it moved at all. "It's like watching the heartbeat of the galaxy," he whispered in an interview. Behind that elegant phrase lay years of quiet determination. At the Chandra Control Center in Massachusetts, engineers spent endless nights keeping mirrors aligned to within microns. Even the vibration of passing trucks could ruin a dataset. In the New Mexico desert, technicians worked through sandstorms to clean the antenna joints of the Very Large Array so that static would not distort the signal. In Chile, high in the Atacama Desert where the air is thin and bitterly cold, the ALMA telescope's 66 dishes turned in unison, capturing millimeter-wave echoes from the galactic core. Each scientist, each technician, fought against Earth's own restlessness to record a motion smaller than a human hair seen from thousands of kilometers away. That motion, though infinitesimal, changed everything we thought we knew about gravity. It proved that even the most massive object in our galaxy is not immune to the influence of what surrounds it. Stars, gas clouds, and even unseen clumps of dark matter all pull on Sagittarius A, each adding a faint tug to a delicate balance. The result is a ceaseless oscillation, so subtle that it took decades to measure, yet so fundamental that it rewrote our sense of cosmic order. The technique that revealed it, very long baseline interferometry, was itself a triumph of patience and coordination. By linking radio telescopes from Hawaii to Spain, from Chile to Antarctica, astronomers created a single planet-sized eye. Atomic clocks kept every dish in perfect synchronization, accurate to a billionth of a second. When radio waves from the galactic center reached those antennas at slightly different times, the data could be compared to pinpoint the black hole's position to within a few micro-arc seconds. Mathematics and human cooperation turned scattered antennas into a precision instrument capable of detecting the galaxy's quietest tremors. Later, the European Space Agency's Gaia mission added a grander perspective. Gaia measured the motion of over 1 billion stars and revealed that the Milky Way and its central black hole drift together through space at about 552 kilometers per second, roughly 2 million kilometers every hour. Even the still point of our galaxy is part of a larger current. As astrophysicist Karen Oberg wrote, "Motion is not something that happens in the universe. It is the universe." In 2022, the Event Horizon Telescope team released the first direct image of Sagittarius A. That glowing, orange ring, blurry, restless, alive, was not a simple snapshot, but the product of hundreds of scientists across 80 institutions coordinating their observations. They waited for simultaneous clear skies on 8 observatories scattered across Earth, recorded petabytes of data onto hard drives, and physically flew them across oceans for calibration. When the image finally came together, they saw what theory had long predicted: a luminous ring of hot plasma orbiting a dark shadow, a portrait of curved space-time itself. But what caught many researchers by surprise was its restlessness. The ring flickered and shifted during the observations, reflecting the turbulence of a black hole that itself is not completely still. It was like seeing the heart of the galaxy breathe, one team member said. The implication of all this is profound. Gravity, the force we think of as the ultimate anchor, is itself relational. No object, however heavy, commands the cosmos alone. Every mass feels every other mass. Every movement sends a whisper through the fabric of space. The Milky Way's center does not rule. It participates. So tonight, if you step outside and gaze at the silver band of the Milky Way, remember that nothing in that shimmering river of light is still. The sun, the earth beneath your feet, the black hole at the galaxy's core, all are drifting together through an endless gravitational dance. Even the most stable point we know is quietly alive. And in that gentle motion lies a deeper mystery. If Sagittarius A trembles because of what surrounds it, then what holds it in place? That question pulls us onward, to the next part of the story, where we ask what truly keeps the black hole still. Sagittarius A, the immense black hole at the center of our galaxy, weighs nearly 4 million times more than the Sun. Its gravity bends light, distorts time, and commands the orbits of billions of stars. Yet even this titan, this object that defines the shape of the Milky Way itself, is not truly still. It quivers. Astronomers call it a gravitational wobble, one of the faintest, most delicate motions ever detected in the heavens. And this story, the story of how humanity found that tiny tremble, begins with patience almost beyond comprehension. In the early 1990s, a small group of astronomers at the European Southern Observatory began watching a cluster of stars near the galactic core. At that time, Sagittarius A was little more than a bright, mysterious radio source. Its true nature was uncertain. The scientists wanted to know whether the stars around it behaved as if they were orbiting something enormous and invisible. If their paths curved sharply, if their speed rose and fell with regular precision, then the invisible thing must be real and unimaginably massive. Among these stars was one that would soon become famous, S2, a blue-white giant about 15 times the mass of our Sun. It races through space at nearly 7,600 kilometers per second, completing a full orbit around Sagittarius A every 16 years, a blink of an eye in cosmic time. When it swings close to the black hole, it is moving so fast that it could circle the Earth in less than a minute. And each time it passes, the light it gives off shifts slightly toward the red, proof that gravity is stretching the space between it and us. In 2002, telescopes across the world watched S2 at its closest approach. Its trajectory curved sharply, its speed spiked, and for a brief moment, astronomers glimpsed the gravitational shadow of an invisible monster. The data confirmed what theory had long suggested. At the heart of the Milky Way sits a supermassive black hole, But when they refined their calculations, something odd emerged. The black hole itself appeared to move, barely but measurably, as if nudged by the very star it was holding captive. To detect such motion required instruments of exquisite sensitivity. Scientists used a technique called interferometry, which combines light from multiple telescopes to achieve resolution far greater than any single mirror could provide. By aligning the signals from observatories like the Very Large Telescope in Chile and Keck in Hawaii, they could pinpoint the star's position to within tens of micro-arcseconds, about the width of a coin seen on the moon. Each orbit of S2 mapped a curve in space-time around the black hole, and when all those maps were layered together, the center itself was not perfectly still. It wobbled. Andreas Eckart, an astronomer at the University of Cologne, was one of the first to describe this motion. "The black hole isn't being moved by much," he said quietly, "but it is being moved by something." That something was the combined gravitational tug of dozens of neighboring stars, 30 or 40 of them, each tens of times heavier than our sun. Their collective mass was enough to make even a 4 million solar mass black hole sway by about 2/10 of an astronomical unit, roughly the distance between the sun and Mercury over thousands of years. Imagine a heavy buoy floating on a restless sea. Each wave a different star's gravity, each push almost imperceptible. Yet together they keep it rocking forever. At the summit of Cerro Paranal in Chile, engineers built one of the most precise eyes ever made, the Very Large Telescope Interferometer, or VLTI. By linking 4 telescopes into one virtual instrument, they created an optical resolution 1,000 times finer than the Hubble Space Telescope. In 2018, its gravity instrument detected subtle redshifts and blue shifts in the light from S2 as it swung around Sagittarius A, direct evidence that Einstein's theory of general relativity held even under such extreme conditions. Hidden inside that same data was another secret. The black hole itself shifted slightly in response, pulled by its orbiting companion. Frank Eisenhower, who led the gravity collaboration, later described what it felt like to witness that movement for the first time. "It was like watching the black hole breathe," he said. Years of effort, merging data from telescopes across continents, syncing them with atomic clocks accurate to a billionth of a second, correcting for every shimmer of Earth's atmosphere, had led to a measurement smaller than imagination, yet vast in meaning. It proved that even the most powerful object in our galaxy does not exist apart from what surrounds it. Other stars like S62 go even further. S62 completes an orbit around Sagittarius A in just 9.9 years, the fastest ever recorded near a supermassive black hole. At its closest point, it moves at nearly 8% of the speed of light, about 24,000 kilometers per second. That tremendous speed creates a gravitational handshake so intense that it slightly repositions the black hole itself. Each encounter adds a tiny twist, a rhythm so subtle it can only be detected with decades of patient observation. Together, these tugs form a quiet heartbeat at the galaxy's center. To ensure these shifts were real and not artifacts, scientists cross-checked the results with independent instruments. Observations from Keck in Hawaii and Subaru on Mauna Kea matched those from the VLTI perfectly. Different telescopes, different algorithms, different nights, all recorded the same drift. The motion was genuine. The implications stretched far beyond Sagittarius A. That tiny wobble revealed the web of gravity that binds stars, black holes, and entire galaxies together. No object stands apart. Every movement is the result of countless invisible forces, perfectly counterbalanced to create the illusion of stillness. What holds the black hole steady is not some fixed anchor, but a symphony of gravitational pulls. Each star, each cloud, each trace of dark matter playing its part in the cosmic harmony. The work demanded extraordinary patience. Astronomers had to wait not years but decades to see the story unfold. A single orbit of S2 takes 16 years. Confirming a full cycle meant watching half a human lifetime pass. They had to trust their instruments and resist the temptation to draw conclusions too early. Only when nature completed her slow choreography could they trace the shape of truth. And when the data finally aligned, what they found was not chaos, but perfect balance. The galaxy's center remains steady only because everything around it is in motion. Stillness, it seems, is just motion in disguise. Neil deGrasse Tyson once said, "The universe is under no obligation to make sense to you." Yet here, it does. Every orbit, every shift, Every pulse of X-ray light fits beautifully into Einstein's equations. What once seemed paradoxical, a moving center, turns out to be precisely how gravity should behave. So if you imagine the scene now, 26,000 light-years away, a blue-white star like S2 whirling through the dark, its light curving and stretching as it passes the black hole. Picture Sagittarius A, leaning ever so slightly toward it, answering its pull, then drifting gently back. The movement is too small for our eyes, too slow for our senses, yet powerful enough to ripple through the entire Milky Way. That is gravity's quiet truth. Nothing holds still, because everything holds everything else. And if even the heart of our galaxy can move, then what, if anything, is the true center of the universe? That is the mystery waiting in the next part of our journey. What if the center of our galaxy isn't truly the center at all? For decades, astronomers believed that Sagittarius A, the supermassive black hole sitting 26,000 light-years away, was the fixed heart of the Milky Way, the point around which everything turned. But when instruments grew more precise and missions like Gaia began charting the stars in three-dimensional motion, a deeper truth emerged. Sagittarius A itself is moving, not randomly, not aimlessly, but as part of a hidden orbit that sweeps the entire galaxy along with it. This hidden motion is called the barycenter, the true gravitational balance point of a system. It's not a single object, not even a visible place, but a position in space defined by all the mass that surrounds it. Earth and the Moon, for example, orbit a shared barycenter located just beneath Earth's surface. Likewise, the Milky Way and every one of its billions of stars orbit a barycenter that lies somewhere between the dense spiral arms and the vast dark matter halo. Sagittarius A doesn't anchor the galaxy, it's part of the dance. NASA and ESA confirmed this in their joint analyses of data from Gaia and Planck. The Milky Way, they found, drifts through space at roughly 552 kilometers per second, moving toward the constellation Leo relative to the cosmic microwave background. Our black hole isn't an unmoving king. It's being carried along by the same flow of gravity that guides the sun, the planets, and every glimmering cloud of dust. Astronomers now visualize the galaxy not as a rigid pinwheel, but as a living river of motion. Each star contributes a small gravitational tug. Gas clouds, dark matter filaments, and distant clusters each add their influence. The result is a shifting barycenter, a balance point that wanders through space like the center of mass in a flock of birds. We orbit together, not around a throne, but around a harmony of motion. The evidence came from two remarkable observatories, Gaia, launched by ESA in 2013, and NASA's earlier missions WMAP and Planck. Gaia's task is deceptively simple: to map the positions and motions of more than 1.5 billion stars with precision better than 1,000th of a degree. By comparing their apparent movements over years, Gaia revealed that the Milky Way is not standing still. The entire disk, spiral arms, and central bulge are gliding toward a point in space known as the Great Attractor, a gravitational anomaly lying hundreds of millions of light-years away. Meanwhile, Planck and WMAP looked outward, measuring the faint afterglow of the Big Bang, the cosmic microwave background. Across the sky, they found a subtle temperature difference. One side slightly warmer, the other slightly cooler. That tiny asymmetry told us that our whole galaxy, including Sagittarius A, is moving relative to the primordial light of creation itself. From that difference, scientists could calculate both our direction and speed. We are, quite literally, sailing through space together at nearly 2 million kilometers per hour. Brent Tully, an astrophysicist at the University of Hawaii, described this motion not as falling but as flowing. "We are not falling into something," he said. "We are flowing along the contours of a gravitational landscape." The phrase captures the truth perfectly. Gravity does not act like a chain pulling us toward a single point. It behaves like the slope of a valley down which entire galaxies drift. Visualize the Milky Way as a vast, rotating disk 100,000 light-years across. At its luminous center glows Sagittarius A, surrounded by swarms of stars and shrouded in gas. But if you could step far enough back to see the entire local group, the cluster of more than 50 galaxies that includes our own and Andromeda, you would notice something else. The Milky Way itself is in motion, orbiting a common barycenter shared with its neighbors, carried by invisible threads of gravity woven through dark matter. Beyond that lies the Virgo supercluster, And beyond even that, the immense structure called Laniakea, immeasurable heaven, a cosmic continent stretching 500 million light-years. Each layer orbits within the next, a cascade of nested movements like shells in an infinite sea. To confirm this hierarchy of motion, scientists built elaborate three-dimensional velocity maps combining radio interferometry and Gaia's astrometric data. Using observatories such as ALMA in Chile and the Very Large Array in New Mexico, they traced the flow of gas clouds and star-forming regions. Each motion added another vector, another arrow in the grand diagram of the Milky Way's drift. The conclusion was inescapable. Even the supposed center is not fixed. The black hole itself is pulled slightly off-center by the uneven distribution of matter across the spiral arms. The galaxy doesn't spin around a single point. It balances upon billions. One of the most striking confirmations came in 2019 from the Harvard-Smithsonian Center for Astrophysics. Researchers there used natural microwave lasers, called masers, emitted from star-forming regions to measure their Doppler shifts. When they mapped those motions in 3 dimensions, they found a consistent direction. Everything in our region of the universe, from Sagittarius A to the most distant hydrogen clouds, is moving together toward a gravitational convergence zone. Even the light from the galactic center bears this signature, its wavelengths subtly stretched by our collective drift. In a quiet laboratory at NASA's Goddard Space Flight Center, scientists compared Gaia's star motion data with Planck's cosmic background measurements. 2 completely different techniques, 2 sets of instruments, yet they pointed to the same truth. The Milky Way's heart is not the true center. It orbits an invisible point of equilibrium shared among galaxies, held together by gravity and dark matter. Behind these charts and equations lies decades of human persistence. Observers in deserts, mountaintops, and space stations gathered fragments of information. Slight shifts in starlight, subtle delays in radio waves, and trusted that the pattern would one day emerge. Their reward was a vision of the universe as a single, interconnected system. Nothing moves alone. Every motion is echoed in another. Carl Sagan once reminded us that we inhabit an ordinary planet circling an ordinary star, lodged between 2 minor spiral arms of a modest galaxy. Yet that modest place participates in a choreography grander than imagination. The Milky Way's core wobbles, the galaxy itself glides, and all of it is stitched into the invisible architecture of space-time. So when we look up at the band of the Milky Way arcing across the sky, we are not seeing a fixed picture. We are looking into a moving stream of light, each star drifting, each photon carrying evidence of that motion. The black hole we once imagined as a motionless anchor is itself caught in the current. And if even the Milky Way's center moves, the question deepens. What is it that guides the galaxy's path through this gravitational ocean? What is this unseen structure that threads all motion together, that keeps galaxies like ours gliding in formation across the universe? That is where the next part of our journey will lead, into the vast gravitational basin that astronomers call the Great Attractor. If even the heart of our galaxy drifts, then where is the Milky Way itself going? That question turns our sense of place inside out. Because the more precisely astronomers have measured our position in the universe, the clearer it has become that nothing, not even galaxies, remains fixed. When we zoom out far enough, the Milky Way, with all its billions of stars and planets, isn't quietly spinning in isolation. It is moving fast. According to measurements from ESA's Gaia mission and NASA's Planck satellite, our galaxy races through space at nearly 600 kilometers per second, headed toward a region known as the Virgo cluster, more than 50 million light-years away. That's over 2 million kilometers every hour. By the time these words have reached you, the Milky Way has already drifted hundreds of kilometers farther across the void. But how do we know that an object so vast, 100,000 light-years across, is moving at all? The answer came not from visible light, but from a faint whisper left behind by the birth of the cosmos itself, the cosmic microwave background. This glow, the cooled echo of the Big Bang, fills the sky in every direction. It should appear perfectly uniform. Yet when satellites such as WMAP and Planck mapped it with exquisite precision, they found one side of the sky slightly warmer and the other slightly cooler. That temperature difference, tiny as it was, revealed a single fact. We are moving through that ancient radiation. The shift isn't random. It tells us that our galaxy, along with its neighbors, is flowing through the universe in a specific direction. NASA scientists describe this movement as a flow, not a flight. We are not being thrown through space like a stone. We are being carried, drawn by invisible gravity towards something immense. For decades, astronomers tried to identify what was causing this drift. When they compared the motions of thousands of galaxies, they noticed a pattern. Instead of moving smoothly apart, as Hubble's law predicted, entire clusters were converging toward one region of the sky, near the constellations Centaurus and Norma. Something colossal was pulling them in. They called it the Great Attractor. In the early 1980s, optical telescopes could see almost nothing in that direction. The dense plane of our own Milky Way, packed with stars, dust, and gas, blocked the view, creating what astronomers call the zone of avoidance. But hints accumulated. Measurements of galaxy redshifts showed that even our local group, including Andromeda and dozens of smaller galaxies, was moving toward the same hidden region. In 1986, astronomers Donald Lynden Bell and Sandra Dressler compiled data from more than 400 galaxies and confirmed a large-scale flow of matter toward Centaurus. The term Great Attractor entered the vocabulary of science and mystery alike. Still, no one could see the object itself, so researchers turned to other wavelengths. Radio telescopes such as Parkes in Australia began scanning the southern sky with 21-centimeter waves, capable of passing through interstellar dust. Bit by bit, a picture emerged. Behind the Milky Way's bright band lay an enormous cluster of galaxies, now known as the Norma cluster, a gravitational knot dense enough to warp the local expansion of space. It was not a single monster, but a region of high density, hundreds of millions of light years wide, where the gravity of countless galaxies combined into a single pull. Later, with data from Gaia and NASA's Cosmic Flows project, scientists refined the map. They learned that the Milky Way and its companions are moving at nearly 600 kilometers per second toward this gravitational basin. Yet beyond the Great Attractor lies something even larger, the Shapley supercluster, containing tens of thousands of galaxies and more mass than words can capture. The Great Attractor, it turns out, may just be the visible edge of a still deeper well in the cosmic landscape. To imagine it, think of space not as empty, but as a vast ocean of density. Galaxies are like leaves drifting along its surface. They do not travel in straight lines. They flow along invisible valleys and ridges sculpted by gravity. In that sense, the Great Attractor is not an object, but a hollow in the cosmic terrain, a deep gravitational valley into which galaxies, including ours, gently slide. The scale of this motion defies imagination. Our solar system orbits the Milky Way once every 230 million years. The galaxy itself drifts toward the Great Attractor over billions. Every orbit, every rotation, every drift we make is part of this immense journey. We are not stationary observers gazing outward at the universe. We are passengers carried by the same current that guides all galaxies. Behind the data lies a human story of relentless precision. At ESA's Operations Center in Darmstadt, engineers working on Gaia had to correct for even the spacecraft's own microscopic wobbles while measuring distant stars. A fluctuation in temperature or a vibration from a solar panel could distort the readings. Each correction demanded new algorithms, new patience, until Gaia could track the motion of stars thousands of light years away to within mere hundredths of a millisecond. When those results were compared with Planck's cosmic background data, the alignment was perfect. The Milky Way's path through the universe became visible, not as a guess, but as a trace drawn in light. It's a sight that humbles every observer. To the naked eye, the Milky Way seems frozen, a luminous bridge across a quiet sky. But that bridge is racing through darkness, stretching space behind it as it goes. Even the sun, steady and ancient in our imaginations, is part of this immense drift, orbiting the galactic core while the entire galaxy slides through intergalactic space. There is no stillness, no up or down, no edge, only motion and curvature. In 2020, the Cosmic Flows 3 project refined the picture even further. By measuring the redshifts and distances of more than 18,000 galaxies, astronomers produced a three-dimensional map of how matter moves relative to cosmic expansion. They found that the Milky Way is indeed traveling toward the Virgo cluster, but slightly offset, as if drawn not only by that cluster's mass, but by another giant region beyond, the Shapley supercluster. itself a gravitational titan, it was like discovering that the great attractor, enormous as it is being pulled by something greater still. Neil deGrasse Tyson once reflected, "We are part of this universe, we are in this universe, but perhaps more important than both of those facts is that the universe is in us." In the motion of galaxies, that thought becomes literal. Every atom, every star, every spiral of light is caught in the same gravitational tide. We drift not by choice, but because space itself is stretching, folding, and flowing around us. Even as you listen now, the Milky Way has moved another few hundred kilometers along its invisible path. The galaxy is not a static collection of stars, but a vessel sailing an ocean of gravity. Sagittarius A does not command that voyage. It shares it. The entire Milky Way, from its glowing arms to its dark halo, is a single traveler pulled toward an unseen destination. And that brings us to the haunting question that remains. What is this vast power drawing us in? What lies behind the curtain of dust and stars? Behind the great attractor's mysterious pull? In the next part of our journey, we will turn our gaze toward the hidden region of the sky that has long resisted our instruments, a cosmic blind spot known as the zone of avoidance. What could possibly be powerful enough to pull thousands of galaxies, including our own, through the universe? This is not a poetic question. It's a genuine scientific mystery that has haunted cosmology for decades. The answer lies in a place that astronomers, for most of history, couldn't even see. They call it the Great Attractor, a name that sounds more like myth than science, yet it's as real as the forces that shape every star and orbit we know. It sits roughly 150 to 250 million light-years away, hidden behind the dense plane of our own Milky Way, in the direction of the constellations Centaurus and Norma. This region is so crowded with stars and dust that optical telescopes go nearly blind when aimed there. Astronomers call it the zone of avoidance, a fitting name for a cosmic secret concealed in plain sight. For decades, the Great Attractor remained invisible, a gravitational ghost whose presence was known only through the way it pulled everything toward it. The story began in the 1970s, when astronomers started measuring the redshifts of galaxies, how much their light was stretched by cosmic expansion. According to the Hubble model, galaxies should move away from one another in all directions, with their speed proportional to their distance. But the data didn't fit. Large clusters of galaxies, including our own local group, appeared to be moving toward a specific region in Centaurus. Something massive, so massive that it distorted the entire expansion pattern of the local universe, was tugging at them. By 1986, astronomers Donald Lynden Bell and Sandra Dressler confirmed it. A huge flow of matter was moving toward one part of the sky. They named the unseen force behind it the Great Attractor. The name stuck, even though no one knew what it really was. Was it a single gigantic cluster, a wall of dark matter, or merely a side effect of something even larger and deeper, hidden behind our galaxy's glare? Throughout the 1990s, scientists across the world tried to peer through the Milky Way's veil. The Parkes radio telescope in Australia began scanning the southern sky using 21-centimeter radio waves, the wavelength emitted by hydrogen atoms. Unlike visible light, these waves can travel through interstellar dust. Slowly, pixel by pixel, an image formed. What it revealed was astonishing. Behind the thick band of our galaxy lay an enormous congregation of galaxies, densely packed into a structure now known as the Norma cluster. This cluster alone contains thousands of galaxies bound together in a gravitational, not so massive that it bends the expansion of the universe around it. It soon became clear that the Great Attractor wasn't a single object but an entire region of high density, hundreds of millions of light-years across. Its gravitational pull extends over tens of thousands of galaxies, including our own. The more astronomers mapped, the more complex the picture became. It turned out that this region was only one node in a still larger structure, the Laniakea supercluster, a vast cosmic continent of over 100,000 galaxies, all connected through rivers of gravity. The deeper scientists looked, the stranger it became. Using the cosmic flows surveys, researchers tracked the three-dimensional motion of galaxies. Each galaxy's velocity, when plotted in space, traced a line toward the same direction, a vast gravitational basin. Within this basin lies the Norma cluster, the heart of the Great Attractor. And beyond that heart, even deeper, sits another colossus, the Shapley concentration, an even larger cluster of galaxies, with more than 10 quadrillion times the mass of the Sun. The Great Attractor, it turned out, might be only the first visible ripple in an ocean of gravity stretching across 500 million light-years. To make sense of it, NASA astrophysicists began describing galactic motion not as straight paths through empty space, but as flows through a cosmic landscape, a terrain sculpted by the invisible hand of gravity. In that picture, galaxies don't fly like bullets. They drift like rivers through valleys and slopes of the cosmic web. The Great Attractor is one of those valleys, a gravitational sinkhole into which the space itself is sliding. Imagine a drop of ink falling into water. The currents pull it gently one way, then another, not because the water wants it to move, but because the shape of the flow leaves it no choice. That's what's happening to us. The Milky Way and its neighbors are being carried along a gravitational current toward an unseen low point in the structure of space-time. The scale of this journey is almost incomprehensible. Our Sun's orbit around the Milky Way takes 230 million years. The Milky Way's path toward the Great Attractor will take billions. Every cycle of the solar system, every rotation of the galaxy, every second of our lives occurs during this long migration through the cosmos. Behind every discovery in this story is human persistence. In 2016, an international team led by Hélène Courtois at the University of Lyon used data from over 8,000 galaxies to chart their three-dimensional motions. By applying mathematical filters that removed random movement, they revealed the true underlying gravitational flow. The result was breathtaking, a map of the local universe showing vast rivers of galaxies converging into one enormous basin. Our Milky Way lay within one of those rivers, flowing gently toward the heart of the Great Attractor. Our home, Courtois said, is much bigger than we thought. Each data point on that map represented thousands of hours of labor, calibration, observation, verification. Each galaxy's position had to be corrected for cosmic expansion, Earth's motion, and relativistic effects. The precision required was staggering, and yet the reward was more than worth it. For the first time, we could visualize the Milky Way's journey as part of a much larger river of motion, an intergalactic current guided by gravity's invisible hand. The Great Attractor remains mysterious, but with every new telescope, the picture sharpens. When the James Webb Space Telescope turned its infrared eyes toward the zone of avoidance, it captured faint smudges of light, distant galaxies, their glow stretched by billions of years of travel. Some of those galaxies appear aligned along filaments of the cosmic web that converge toward the Great Attractor. Even after all this time, the flow persists. The pull continues. What's most humbling is that we can't yet see what's doing the pulling. Even now, the region is partly obscured. Gravity reveals what light cannot. Astronomer René Cran-Korteweg, one of the pioneers in mapping it, once said, "We are still blind to what lies beyond the dust, but gravity is not." That sentence captures the wonder of it all. We don't need to see to know it's there. The universe itself shows us through motion. As we drift toward that gravitational valley, we are part of something unimaginably vast, a cosmic stream connecting us to thousands of galaxies. It's not chaos, it's structure. Each cluster, each filament, each thread of dark matter forms part of the same web. And somewhere, deep within that web, lies the reason we move at all. The Great Attractor is not a monster made of matter. It is a curvature in the geometry of the universe, a silent basin in the fabric of space. Everything that has mass feels its presence, even across hundreds of millions of light years. Every galaxy, every cluster, every star is drawn by that quiet, invisible slope. So when you look up at the night sky and see the Milky Way glowing across the darkness, remember that it isn't resting there, it's gliding, carried by a gravitational current older than time itself. And as our galaxy sails toward that hidden destination, we can only ask, what lies beyond it? Beyond the reach of the Great Attractor, beyond the regions our instruments can yet see, that is where we go next, to the zone of avoidance itself, the hidden curtain of the cosmos, where light still struggles to reveal the full truth of the universe's pull. The zone of avoidance. Even the name carries a hush, as if the cosmos itself were warning us not to look too closely. For much of astronomical history, this region of the sky, where the plane of our Milky Way cuts across our line of sight, was a blank on every deep space map. Not because nothing lay beyond, but because everything was hidden. Clouds of gas, billions of stars, and vast bands of cosmic dust blocked our view, swallowing the light from galaxies that might have revealed the universe's deepest secrets. It was the greatest blind spot in all of astronomy, and it sat directly between us and the source of the Great Attractor's pull. For a long time, astronomers had no choice but to look elsewhere. Optical telescopes could see almost nothing in that direction. The dust was simply too thick. Photographic plates taken in the mid-20th century showed only a narrow smear of dim starlight, and beyond that, darkness. But the clues were irresistible. Redshift surveys kept showing the same anomaly. Galaxies on both sides of the Milky Way appeared to be moving towards something massive hidden behind the plane. Whatever was concealed there, it was powerful enough to bend the expansion of the local universe itself. By the late 1980s, scientists began to attack the problem from a new angle. If visible light couldn't escape the dust, perhaps radio waves could. The Parkes Radio Telescope in Australia began a bold experiment, scanning the southern sky at a wavelength of 21 centimeters, the signature of neutral hydrogen. Unlike visible light, these long waves can slip through dust and gas with little interference. Night after night, the telescope traced invisible arcs across the hidden sky, listening for the faint echoes of distant galaxies. It worked. Slowly, patiently, a new map began to form. Where optical images had shown nothing, the radio map filled with points of emission, galaxies long obscured, each one a beacon whispering through the cosmic fog. By the 1990s, hundreds of hidden galaxies had been catalogued in the zone of avoidance, many belonging to the Norma cluster, the dense heart of the Great Attractor. For the first time, humanity could glimpse what lay beyond the Milky Way's veil. The Norma cluster sits about 200 million light-years away, a colossal concentration of matter roughly 10 times the mass of the Virgo cluster. It is a maelstrom of galaxies colliding and merging, their gravitational fields intertwining to form one of the deepest wells in the known universe. Every spiral and elliptical galaxy there orbits a common gravitational center, creating a giant vortex that influences the motion of galaxies hundreds of millions of light-years beyond. The Great Attractor, it turns out, isn't a single point. It's an entire region dominated by structures like the Norma cluster, where gravity warps the cosmic landscape itself. To see this invisible world required not only technology, but imagination. Astronomers combined data from radio, infrared, and X-ray telescopes, layering them into three-dimensional reconstructions. The Infrared Astronomical Satellite, IRAS, had already revealed that dust itself glows faintly in infrared light, which meant that, paradoxically, the very substance that hid these galaxies could also help find them. Using infrared data to trace where the dust was thickest, scientists could compensate for its blocking effect and correct their maps. Later missions, such as NASA's WISE, Wide Field Infrared Survey Explorer, took the process further. WISE scanned the entire sky in infrared, uncovering hundreds of thousands of new galaxies in regions that had once been empty. Each new detection refined the shape of the gravitational basin pulling us forward. The Great Attractor was no longer a ghost. It was a living structure, and the zone of avoidance was its curtain. Among the scientists working on this frontier was Renée Cran-Korteweg, whose decades-long effort to map hidden galaxies turned patience into art. She often described her work as cartography of the unseen. With every new survey, she and her colleagues peeled back another layer of obscurity, revealing clusters, filaments, and bridges of galaxies spanning the invisible space behind the Milky Way. The image that finally emerged was breathtaking, a vast, interconnected tapestry of matter, stretching like a river system across the universe. Our galaxy was just one drop in that cosmic flow. The breakthrough came when scientists combined these galactic maps with the velocity data from the cosmic flow surveys. The pattern of motion matched perfectly. Everything around us, including the Milky Way, was sliding toward the same hidden basin behind the zone of avoidance. The Norma cluster was its core, but the true gravitational center extended beyond it, toward the even more massive Shapley supercluster further away. The Great Attractor, once thought to be the final destination of our galactic motion, was revealed to be just one step in a much larger cascade of gravity. The zone of avoidance still hides much of this structure. Even with modern telescopes, dust and star fields block nearly 20% of the sky. But technology keeps evolving. Infrared detectors grow more sensitive. Radio arrays like Meerkat in South Africa and ASCAP in Australia now map the hydrogen emission of galaxies across billions of light years. And space observatories such as the James Webb Telescope can see further through the dust than ever before. Piece by piece, the curtain is being drawn back. What these observations reveal is astonishing. Behind the visible Milky Way lies a web of galaxy clusters interconnected by filaments of dark matter and hot gas. This web isn't random. It forms the skeleton of the universe. The Norma cluster, the Great Attractor, and the Shapley supercluster are all part of this cosmic architecture. We are moving not because of one mysterious object, but because of the shape of space-time itself, the uneven distribution of matter carved by gravity since the dawn of time. Each discovery reminds us how small we are in this vast, invisible structure. Our planet, our sun, even our entire galaxy is just one thread in a cosmic web that spans billions of light years. And yet, through fragile instruments and patient observation, we can trace those threads, map their flows, and glimpse the architecture of the universe itself. The Great Attractor is no longer merely an unseen force. It's the beginning of a revelation that the entire universe is connected through invisible filaments of gravity and dark matter, forming a cosmic network so vast that no galaxy truly stands alone. As our instruments continue to pierce the veil of the zone of avoidance, we begin to see that the mystery doesn't end there. The Great Attractor and the Norma cluster are not the ultimate centers. They too are being drawn onward by something deeper, something grander. The pattern continues, pull upon pull, motion upon motion, layer upon layer, until the question becomes impossible to avoid. If everything is being pulled by something larger, what is it that all of it moves within? Is there a final anchor, a true still point in this web of motion, or is motion itself the only constant? That question carries us beyond visible matter and even beyond the galaxies themselves, into the invisible realm that binds everything together, into the shadowy architecture known as dark matter. When the veil of the zone of avoidance began to lift, astronomers realized that what they were seeing, the Norma cluster, the Great Attractor, the hidden filaments of galaxies, was only a fraction of the story. The visible universe, bright as it is, makes up less than 5% of what truly exists. The rest, the unseen scaffolding that holds everything together, is invisible. It neither emits nor reflects light, yet it dictates how galaxies form, how they move, and even how the universe itself expands. They called it dark matter, and it may be the true reason the Milky Way, Sagittarius A, and every other galaxy drifts through space in their quiet, endless orbits. The idea of dark matter isn't new. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster of galaxies and found that the galaxies were moving too fast to be held together by their visible mass. Something unseen was providing extra gravity, enough to keep the cluster from flying apart. He called it Dunkelmaterie, dark matter. Decades later, the American astronomer Vera Rubin confirmed this at a smaller scale. When she measured how fast stars orbit around the centers of galaxies, she found that those on the outskirts moved just as quickly as those near the middle. According to Newtonian physics, they should have been slower, or the galaxies should have torn themselves apart. The only explanation was that a massive halo of invisible matter surrounded each galaxy, holding it together with gravity we could not see. Today, we know that these halos are everywhere. They extend far beyond the luminous disks of galaxies, forming vast overlapping spheres that connect through cosmic filaments stretching across the universe. The Milky Way's own dark matter halo is thought to be more than 1 million light-years wide, dwarfing the visible spiral of stars. Sagittarius A, that brilliant gravitational heart of the galaxy, is only one node in a much larger invisible framework. What we see as the Milky Way's body, the stars, gas, and nebulae, is just the faint, luminous skin of an enormous dark structure. This hidden skeleton changes how we understand motion itself. The Milky Way's drift toward the Great Attractor is not simply a fall through space. It's a response to the curvature of gravity woven by dark matter. When astronomers simulated the large-scale structure of the universe, starting from the conditions after the Big Bang, the result was a vast web. Filaments of dark matter formed first, then pulled in ordinary matter, creating rivers of galaxies that flow along these unseen paths. The Great Attractor, the Shapley supercluster, even the Laniakea Basin. Each is just a deeper valley in this grand landscape. To detect something invisible, scientists turned to its influence. Gravitational lensing became their tool, a phenomenon predicted by Einstein's general relativity, in which massive objects bend light from objects behind them. When light from distant galaxies passes through a region rich in dark matter, it is subtly distorted. By mapping those distortions, astronomers can reconstruct where the invisible mass lies. The Hubble Space Telescope, the Subaru Observatory, and later, the Dark Energy Survey, have used this technique to reveal a ghostly network of mass-connecting galaxy clusters. Each curve of bent light traces an unseen hand pulling on the fabric of space-time. In 2021, the European Space Agency's Gaia mission added new depth to this picture. By precisely tracking the motion of over 1 billion stars, Gaia allowed scientists to infer the distribution of dark matter within the Milky Way. The results were extraordinary. The data showed that our galaxy's stars, including those near Sagittarius A, move in patterns that only make sense if the dark matter halo is both immense and uneven. The halo itself is slightly lopsided, its density higher on one side, perhaps because of gravitational interactions with the nearby Andromeda galaxy or with invisible streams of dark matter that thread the local group. This imbalance could even explain why Sagittarius A wobbles ever so slightly in its position. The black hole isn't truly off-center. It's responding to the asymmetry of an invisible sea. In the stillness of an observatory at night, scientists know this truth deeply. What we can see is only a trace of what exists. The stars and galaxies, the glowing nebulae, the X-ray bursts from black holes. All of it is just the luminous foam on a vast dark ocean. The real structure of the universe lies beneath, where gravity sculpts the cosmic web. Every visible motion, from the path of a single star to the drift of entire galaxies, is shaped by that unseen architecture. To picture it, imagine space as a transparent honeycomb. The edges of the cells are filaments of dark matter, and where they intersect, galaxies form like dewdrops clinging to the web. Between the filaments lie voids, enormous empty regions millions of light years across where almost no galaxies exist. The Milky Way sits within one of these filaments, drawn ever onward by gravity's gradient toward denser regions. The Great Attractor is one of those denser knots, but it too is embedded within the same dark framework. Dark matter does not interact with light, but it interacts with gravity. That means everything with mass feels its pull, even though we cannot detect it directly. It is, in a sense, the silent composer of the universe's symphony. Without it, galaxies would not have formed. Stars would not have coalesced, and Sagittarius A itself might never have come into being. Dark matter doesn't just anchor the Milky Way, it gives the galaxy its shape, its stability, and even its motion. And yet, as vast as this unseen substance is, it accounts for only about 27% of the universe's total energy content. The rest, nearly 70%, is something stranger still. Dark energy, the force driving the accelerated expansion of the cosmos. If dark matter pulls, dark energy pushes. The two exist in constant tension, balancing the cosmic architecture like the inhale and exhale of existence. Every discovery brings us closer to understanding that balance. The Milky Way's movement, the Great Attractor's pull, and the cosmic expansion aren't separate phenomena. They're expressions of the same underlying structure. Dark matter shapes the web. Dark energy stretches it. One sculpts, the other breathes. Together, they create a universe that is both bound and unbound, anchored and expanding. To stand under the night sky and think about this is to feel both humbled and infinite. The stars overhead seem so permanent, yet they are merely momentary lights drifting along invisible tides. Even the black hole at our galaxy's center, once thought to be the ultimate anchor, is just a buoy bobbing on the surface of a sea of dark matter. The scientists who study this invisible realm often speak of wonder, not fear. They know that our ignorance isn't a flaw, it's an invitation. Every new detection, every faint distortion of light, every subtle vibration of space brings us closer to seeing the skeleton of reality itself. But as we uncover more, another question emerges, one that stretches beyond gravity, beyond matter, even beyond the visible and invisible. If dark matter defines the shape of the cosmos, and dark energy drives its expansion, what gives rise to the entire web they inhabit? What underlies the stage upon which all motion unfolds? To find that answer, we must step back even further, beyond galaxies, beyond clusters, to the structure of the universe itself, a place where the cosmic web becomes a single, breathing organism, the place where motion and stillness merge into one. When astronomers finally mapped enough of the universe to see the larger picture, what they found was something so intricate and vast that it felt almost alive. It wasn't a random scattering of galaxies, nor a neat spiral of order. It was a vast network of filaments, threads, and voids, stretching hundreds of millions of light years in every direction. They called it the cosmic web, a name that feels poetic, but it's also literal. It is the true architecture of everything. Every galaxy, every cluster, every black hole, even Sagittarius A, is a single particle in that immense structure, moving as part of a universal flow. This web wasn't discovered all at once. Its existence emerged gradually, piece by piece, as technology caught up with imagination. The Sloan Digital Sky Survey, beginning in the late 1990s, mapped the positions of over 1 million galaxies. When those positions were plotted in 3 dimensions, they didn't form a uniform field. They outlined long filaments of matter weaving between enormous empty regions called voids. Galaxies are not evenly distributed across the universe. They trace the threads of invisible dark matter that formed first, long before the first stars ever shone. Within those filaments, galaxies cluster like droplets on strings. Each node where filaments intersect contains massive structures, superclusters of galaxies, each home to thousands of Milky Way-sized systems. Between those filaments lie the voids, expanses of almost perfect emptiness where matter is scarce and light travels for hundreds of millions of years without encountering a single star. These contrasting realms, dense filaments and vast voids, create the texture of the cosmos itself. Our Milky Way lives in one of these filaments, part of a grander structure called the Laniakea supercluster. The name means immeasurable heaven in Hawaiian, and it's as fitting as any word could be. Laniakea spans about 500 million light-years and contains roughly 100,000 galaxies. The Milky Way sits on its outer edge, drifting slowly along one of its gravitational rivers toward a region called the Great Attractor, which forms Laniakea's core. The discovery of this supercluster redefined our cosmic address. We aren't simply part of the Milky Way, or even the local group. We belong to a vast cosmic continent, one among countless others. To visualize Laniakea, scientists used the Cosmic Flows dataset, measurements of galaxy velocities combined with redshifts. Each galaxy's movement was represented as a tiny arrow, showing the direction and speed of its drift. When thousands of these arrows were plotted together, a pattern appeared. Galaxies weren't moving randomly, but following curved paths, converging toward shared centers. The flow lines resembled the drainage system of a continent, with each river of galaxies leading toward a deeper gravitational basin. The Great Attractor was one of those basins, and our own Milky Way was part of a stream feeding into it. At the boundary of Laniakea, the arrows change direction. They point away, flowing toward neighboring superclusters like Perseus Pisces and Coma. These borders are not walls, but gentle gradients, where gravitational influence fades and another takes over. The universe, it turns out, is a patchwork of these interconnected basins, each a gravitational watershed draining toward its own low point. The recognition of Laniakea shifted astronomy from thinking in isolated galaxies to thinking in flows. Gravity doesn't just pull, it organizes. The same invisible forces that make stars orbit Sagittarius A also shape the motion of entire clusters. It's all one system, operating on scales beyond comprehension. The cosmic web isn't static either. It's evolving. Over billions of years, galaxies merge, clusters collide, and dark matter filaments thicken as gravity pulls them tighter. At the same time, the expansion of the universe, driven by dark energy, is stretching those filaments apart. In the delicate balance between these two forces, gravity's inward pull and dark energy's outward push, the universe breathes. This motion isn't metaphorical, it's measurable. Astronomers have observed galaxies moving apart faster than before, proving that expansion itself is accelerating. The paradox is beautiful. The same cosmos that is bound together by invisible threads is also being stretched wider every second. On the largest scales, there is no center and no edge, only expansion. Every galaxy sees itself as the center of this motion because the fabric of space is stretching equally everywhere. In that sense, the question, what does Sagittarius A orbit, becomes almost poetic. It orbits nothing and everything at once. It's part of a motion so vast that no single object can define it. Imagine the universe as a rising loaf of bread, with galaxies embedded in it like raisins. As the dough expands, the raisins move apart, not because they're flying through space, but because the space between them is growing. That is the expansion we live in. The Milky Way, the Great Attractor, even the entire Laniakea supercluster, all are raisins in that cosmic dough. The galaxies are not traveling through space. Space itself is expanding between them. This revelation reframes everything we once believed about motion. When we say a galaxy moves, we don't mean it's speeding through a static void. We mean the geometry of the void itself is changing. The web is alive with tension, expansion, and flow, like a breathing organism. The densest regions, where gravity dominates, grow denser. The empty regions grow emptier. The contrast sharpens with time, sculpting the universe into sharper relief. And still, amid that expansion, every structure remains bound within its own gravity. Our galaxy will not be torn apart by cosmic growth. It's held together by its halo of dark matter. The local group, Milky Way, Andromeda, and their satellites, will stay together as well, eventually merging billions of years from now into a single elliptical galaxy. The larger cosmic web stretches, but the local filaments remain intact. Gravity guards its own within its domain. To the human mind, these scales are impossible to truly grasp. Yet, there's something deeply human in the way we keep trying. We build telescopes, measure faint redshifts, map invisible halos, all to glimpse a system that dwarfs comprehension. Each new discovery feels like pulling back another curtain, only to reveal that the room is bigger than the last. When you stand under the night sky and see the faint smear of the Milky Way, remember that you are looking at a single strand in a web that spans the universe. That faint band of light, made of hundreds of billions of stars, is moving as part of a stream that curves across hundreds of millions of light years. It is one of countless rivers of galaxies flowing through the cosmic landscape. Even now, the Milky Way continues its slow drift through Laniakea, drawn toward the Great Attractor, which itself may be sliding toward the Shapley supercluster, which may be pulled towards something even larger still. The web doesn't end, it only deepens, and through it all, every galaxy, every cluster, every atom participates in the same grand choreography. When scientists say the universe is expanding, it might sound abstract, but in truth, it's an intimate idea. Every heartbeat you feel, every moment that passes, occurs in a space that is literally growing larger. We are not watching the expansion from the outside. We are inside it, carried along with it, part of its rhythm. The cosmic web isn't out there. It's around us, within us, beneath our very existence. And as the universe continues to expand, one question remains unanswered. If everything is connected, if every motion is part of this living web, then what does the web itself rest upon? Is there a center to this infinite structure, or does it too drift in something larger still? That is the question that takes us to the edge of cosmology itself, into the paradox where motion and stillness become the same thing, where gravity and geometry merge into one continuous fabric, space-time. The deeper scientists explored the universe's structure, the more they realized that motion and stillness are illusions created by perspective. When you stand on Earth, it feels as if the ground beneath you is solid and unmoving, but the planet is spinning at over 1,000 kilometers per hour. The Earth orbits the Sun at 30 kilometers per second. The Sun orbits Sagittarius A at 230 kilometers per second, and the Milky Way itself drifts through the universe at more than 500 kilometers per second. Everything moves. Every atom, every star, every galaxy is part of an endless chain of motion. But as we zoom out, beyond galaxies, beyond clusters, beyond superclusters, another truth emerges. The universe has no center. It expands everywhere, equally, in all directions. There is no fixed point, no cosmic anchor, no privileged location around which all else revolves. The very question, what does Sagittarius A orbit, dissolves, because orbit implies a center, and in a universe without one, everything is both center and motion at once. To understand this, we must look back to the beginning, to the Big Bang, the moment when space itself began to expand. Contrary to what many imagine, the Big Bang didn't happen at a single point in space. It happened everywhere, all at once. Every point in the universe today was once part of that same explosion of creation. When we observe galaxies moving away from us, it's not because they're flying through pre-existing space. It's because the space between us and them is expanding. The universe isn't expanding into anything. It's simply creating more of itself. That expansion continues today, and it defines the motion of everything we see. Astronomers call it the Hubble flow, the steady drift of galaxies carried by the stretching of space-time. On the largest scales, this flow overwhelms all local motion. The Milky Way's orbit around Sagittarius A, our journey toward the Great Attractor, the pull of the Shapley supercluster, all of it rides atop the cosmic expansion like ripples on a rising tide. To visualize this, imagine a vast balloon covered with tiny dots. As the balloon inflates, every dot moves away from every other. No dot sits at the center. All are equally adrift. From any one of them, it appears as though everything else is receding. But the truth is that the expansion is uniform. This is our universe. Wherever you are, on Earth, near another star, or in a distant galaxy, the cosmos looks the same in every direction. There is no edge, no outer boundary, no fixed frame of reference. The discovery of this expansion changed everything. In the 1920s, Edwin Hubble observed that galaxies farther from us were moving away faster. The relationship was linear, double the distance, double the velocity. It was as if the fabric of space itself was stretching. Later, the discovery of the cosmic microwave background confirmed it, the afterglow of the Big Bang, still faintly visible as a uniform bath of microwaves filling the entire sky. This radiation is the same everywhere, down to 1 part in 100,000, proving that the universe is both homogeneous and isotropic on its largest scales. But there is something even stranger. The expansion isn't slowing down. It's accelerating. In 1998, 2 teams studying distant supernovae discovered that galaxies were receding faster than expected. Some unseen energy was pushing the universe apart. That force was named dark energy, and it makes up nearly 70% of the cosmos. Its nature remains one of the deepest mysteries in physics. It acts like negative gravity, an intrinsic pressure of space-time that causes expansion to speed up over time. This acceleration means that distant galaxies are not merely drifting, they are being carried beyond reach. In billions of years, light from many of them will no longer be able to reach us at all. The universe will become increasingly empty from our perspective, its outer edges slipping over a horizon we can never cross. Motion, once a dance of mutual attraction, becomes a separation. The farther things are, the faster they flee. And yet, within this grand expansion, smaller systems remain bound. Gravity holds galaxies together, binds stars to their orbits, keeps planets circling their suns. Within each gravitational pocket, the expansion is invisible. Space itself may be stretching, but the bonds of mass and gravity overpower it locally. Sagittarius A, our solar system, and even the atoms in your body resist that cosmic drift. You are, quite literally, a region of space where expansion has been temporarily subdued. This duality, expansion and binding, motion and stillness, is what defines the universe. Everything moves, yet everything is connected. The Milky Way may race through space, but to us, it feels stable. We orbit Sagittarius A, yet the black hole itself is carried along by the galaxy's larger motion, which is carried by Laniakea, which is carried by the cosmic web, which is expanding without limit. There is no single answer to what anything orbits, because the universe is not built around hierarchies, it's built around relationships. Einstein's general relativity explains this perfectly. Mass and energy tell spacetime how to curve, and spacetime tells mass how to move. There is no absolute motion, no fixed background, only geometry. When we say Sagittarius A sits at the center of the Milky Way, we mean it in a local sense. It defines the curvature of spacetime within our galaxy. But even that curvature rides atop larger ones nested endlessly until they blur into the overall geometry of the cosmos. Some physicists go further, suggesting that motion itself may be an illusion born from how we perceive time. In the block universe interpretation of relativity, past, present, and future all coexist as a single four-dimensional structure. Nothing truly moves. Everything simply is. The flow of time, the expansion of space, the drift of galaxies. These are not changes unfolding in real time, but relationships written into the structure of space-time itself. What we experience as motion is our consciousness moving along one path through that eternal fabric. To think of the universe this way is dizzying, yet strangely comforting. There is no edge to fall off, no center to lose. We are not orbiting a single anchor, but participating in a grand continuum where motion and stillness are the same thing viewed from different scales. Sagittarius A does not orbit something larger. It follows the curvature of space-time that arises from all the mass and energy in the universe. And because that curvature is everywhere, its motion is universal. So, when you look at the stars tonight, realize that they are not standing still, nor are you. The atoms in your body are carried by Earth's orbit, by the sun's motion, by the Milky Way's drift, by the Laniakea supercluster's flow, by the expansion of space itself. You are not separate from the universe's motion. You are part of it, a pattern of matter and energy embedded in spacetime's ever-changing geometry. Every second, every breath, every heartbeat happens inside that geometry. Time is not a river flowing past us. We are part of the river, shaping it as it shapes us. In that sense, there is no need to ask what Sagittarius A orbits. It orbits everything, and everything orbits it. Because the universe itself is one continuous, interwoven motion, a dance without center, without edge, without end. And yet, there remains one final layer to explore, the question beneath all others. If motion is everywhere, if every object follows the curvature of space-time, then what gives rise to space-time itself? What breathes existence into the fabric that holds it all? That question takes us to the final step of this journey, where science meets philosophy, and where motion becomes the language of existence itself. If motion exists everywhere, then what does it truly mean to move? The more we've searched for a final reference point, a still, absolute center, the more the universe has refused to give us one. What began as a quest to understand what Sagittarius A orbits has brought us to a revelation both humbling and extraordinary. There is no fixed anchor. There is only motion woven into the very geometry of reality, a motion that doesn't need a mover. Einstein's general relativity taught us that space and time are not passive backgrounds where events unfold. They are dynamic, responsive, and alive. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. It's not that Sagittarius A is being pulled through an external void. It is following the geometry of spacetime created by everything else. And that geometry is itself shaped by Sagittarius A. The black hole doesn't orbit a thing. It participates in a conversation with the universe's structure. If we could see spacetime directly, we wouldn't see empty darkness. We'd see an endless field, rippling with waves, bending and flexing where mass gathers, twisting where energy moves. Every planet, every star, every cluster creates dimples in that field. When light passes near those dimples, it curves. When a black hole merges, it sends gravitational ripples through spacetime itself, tiny vibrations that instruments like LIGO and Virgo can now detect. These waves are the whispers of the universe breathing. Even gravity, the most familiar of forces, may not be a force at all. In Einstein's picture, it's simply the path that everything follows when spacetime bends. What we feel as the pull of the Earth beneath our feet is our body's resistance to following a curved path through spacetime. When the Earth orbits the Sun, it isn't being pulled around, it's traveling straight through a warped geometry. The same is true for the Sun around Sagittarius A, and for the Milky Way within the cosmic web. None of them are forced to move. They simply exist in a geometry that demands motion. Quantum physics complicates this picture further. On the smaller scales, space-time is not smooth. It flickers and foams, seething with energy even in perfect vacuum. Virtual particles blink in and out of existence, borrowing energy from the void for fractions of a second before returning it. The universe, it turns out, cannot truly rest. Even what we call empty space vibrates with potential. The cosmic background radiation, the faint afterglow of the Big Bang, is a fossil imprint of that first moment of quantum motion stretched across eternity. Physicists searching for a theory that unites quantum mechanics with general relativity suspect that space-time itself may emerge from something deeper, perhaps a web of information, a network of quantum relationships. In that view, motion is not the travel of objects through space, but the continuous rearrangement of these relationships. The universe isn't a stage where things happen. It's an event that is always happening. And yet, despite all this complexity, something in it feels profoundly simple. We move because movement is the natural language of existence. From the vibration of atoms to the spin of galaxies, from the orbit of Sagittarius A to the stretching of the universe, everything participates in one unbroken rhythm. The cosmos doesn't need a center, because every point in it is a center, a place where the universe experiences itself. Imagine standing beneath the night sky. Every star you see, every flicker of distant light, is part of the same geometry that carries you. The photons entering your eyes have traveled for tens of thousands, even millions of years, weaving through curved space-time shaped by invisible masses. And yet, when they reach you, they arrive not as relics of the past, but as proof that motion connects everything. That light is the universe in transit, a message from one region of reality to another. Sagittarius A, the immense black hole that anchors our galaxy, moves through this geometry just as we do. It is a node in the network, a whirlpool in space-time. Around it, billions of stars orbit in stately precision. Beyond it, the Milky Way drifts through Laniakea. Beyond that, the superclusters stretch and flow across the cosmic web. Nothing stands alone. Motion ties all of it together, a silent current carrying galaxies like leaves on a boundless sea. In this light, the question, what does Sagittarius A orbit, becomes almost poetic. It orbits motion itself. It follows the curvature of the universe's story, just as every particle and every thought does. Even consciousness, your awareness reading these words, is a flow, a movement through time shaped by memory and anticipation. You are, in a very literal sense, a wave in the same cosmic sea that carries stars. There's a quiet symmetry in this realization. The universe doesn't revolve around us, nor around any other object. Yet we are not insignificant. We are expressions of the same laws that govern black holes and galaxies. The patterns that shape the cosmos also shape our minds. We are motion becoming aware of itself, starlight folded into thought. So tonight, when you look up and see the Milky Way spread across the dark, remember its center, the glowing core where Sagittarius A dwells, is not fixed. It moves through space that is itself in motion, carried along by gravity, by expansion, by the breathing of space-time. And you, standing beneath it, are part of that same movement. The atoms in your body were forged in ancient stars that once orbited that drifting heart. Their paths have brought them here, to this moment, to this awareness. There is no still point to find, no ultimate orbit to trace. The universe doesn't revolve around something else. It revolves within itself. Space and time are not containers. They are the dance. Welcome to Science Reshaped, where even the question of what moves, what becomes a meditation on being. If this quiet journey through the cosmos brought you a sense of wonder, remember to subscribe to Science Reshaped and tell us where you're listening from. Somewhere, beneath the same stars, another mind drifts through these same thoughts, carried by the same current. Because in the end, everything moves together. Everything orbits everything, and motion itself is the universe's way of being alive.